I don't know how this works. I started the recording just in case this is interesting.
So we're getting into it. So Seve's just brought up a PCB from a satellite. It's RF PCB. So they're a domain of their own, and the components are often basically just traces.
Yeah.
They're embedded components, which you sometimes do in other domains as well. But in RF, it's the only way to do a lot of stuff, it seems. You can see some of these, this is crazy. So some of these like intercombed sections here, they're all sorts of types of various filters, remixes. I'm actually not sure, but I'd love to see what ChatGPT has to say about it.
Yeah, so I had no idea what was going on when I first saw this. And then I just asked ChatGPT, like, what is it? And it told me basically every part. It like really broke it down. Local oscillator, didn't know what that was. So basically this is, as you kind of said, like basically a bunch of antenna filtering, power management stuff. But it's just cool that this stuff is so accessible, because like how else would you get an answer to that? You know,
you go ask your really nerdy friend.
You would need a very, very nerdy friend. Exactly. And now everybody has their nerdy friend.
And now everyone has a nerdy friend. Aww.
Okay, sorry for jumping in so quick, but I was very excited when I...
No. Well, we just started the recording mid-jump because we didn't want to get into it too much beforehand. Seve, how you doing?
Very good, very good.
I'm glad. One thing I realized that we kind of goofed up with a little last episode, we only got to point number 4 or so of your 13 points of auto routing. And honestly, I was quite interested in going through them.
13 things I would have told myself before building an Autorouter. We went through the last 3 points last time. So what's point number 4 here? Effective spatial partitioning and caching is 1,000 times more important than algorithm performance.
That makes sense. How are you doing your caching?
You know what's funny is I wrote so much of this stuff, but we actually don't have that much caching like integrated right now into the algorithm itself. But we have built caching so to understand why I even wrote this, we have to like look at the history. I didn't want to build an Autorouter.
Okay.
I did not want to build it. And I wouldn't even consider myself like an algorithms guy. Like, we were like the biggest sponsor of free routing, and we were trying to get free routing to be this kind of like universal foundation layer for Autorouters.
And we appreciate it.
Yes. I mean, free routing's great. For like decades, it's been the main free auto routing solution, or
free is
maybe
in beer
a little bit
and
less
free
than
is in freedom.
Yes, yes. And so we were we're integrating it. We were working with the maintainer. We helped get the Docker file released for free routing so that anybody can run free routing and talk to it via API.
Yeah, heck yeah.
So we were building this. We launched a free routing cluster, and then we just noticed that it was taking a while to get your results back, and that just kind of created friction.
Yeah.
So we still sponsor free routing, and I still really want that project to succeed. I'm talking to the maintainer, and we're even going to establish like criteria for how to grade Autorouters.
Wow, benchmarking. Universal benchmarking is so valuable.
Yes, it just having a way to say so. And when you get into that, you realize people have very different concerns and considerations when building Autorouters. But which we could talk about. But caching, why do I think caching is so important? The only time we started feeling like the Autorouter, like tscircuit was fun to use with the Autorouter, was when we started doing like caching for subcircuits when using free routing, because then you were getting instant results for at least parts of your circuit, and then it would connect those things together. So that was really powerful. That sped up everything.
Yes.
And then you have to wonder, like, how much can that concept just be applied to not the full auto routing process, but like little subsections and stuff like that. And effective caching is actually pretty hard.
Yes, extremely.
It's super hard. Like if you have a subcircuit that's moved around, that should be cached the same way no matter where it is, if it's on bottom or top layer. Yep. So you kind of have to have very special caching to get it to work. But when you get it to work, it's very rewarding.
That's awesome. Because, I mean, you are talking about like thousands of times speed up, likely. Because if you have particularly with a tree of caches, you've got like the sub-modules cached and then the modules that they're within cached. Some, let's say, first route to try, perhaps, for the actual routing cache. And so you have a starting place and you only need to walk backwards a little bit.
Yep.
Like I can imagine that being incredibly important.
Yeah, absolutely. One of the most, a lot of our Autorouter spends time optimizing. And so we want to cache a lot of the optimizations.
Yep.
We haven't written a lot about this yet, but we do this thing that I call unraveling.
Okay.
Because I thought that was a cool word. By the way, unravel is a very interesting word because it means the same as ravel. It's like one of those things. But anyway, we do this thing we call unraveling, which is where we optimize to kind of like de-twist. If you imagine traces as being wires, we try to de-twist them. And it's very cacheable. Like, if you have a wiring configuration, you can just remember it. And what this graph presents is that storage costs and the size of our cache is getting bigger and bigger, and it's cheap to store in cache. But computation is, I drew it as linear. It's not, maybe not quite linear, but it's not really the same as a cache. If you get a really big cache and you get it working, you should be able to get instant auto-routing algorithms, which is our
Holy grail. Yeah, incredible.
Yeah, so that's caching. If you don't have a visualization for a problem, you'll never solve it. Too many people like stare at numbers and they use that to debug. Just build a visual, especially with Claude. A lot of times if you're debugging a small algorithm, you could just have Claude recreate your algorithm. Even if your source code's in Python, give it to Claude and say, rewrite this in JavaScript and execute in a browser.
You can do that, but God, is there just a few little things that make this type of thing so much easier? So my domain, typically Python. Yesterday I was having a problem with GitHub Actions OIDC tokens.
Oh,
do you know anything about this?
OIDC is OpenID, is that right?
Yes, it was OpenID Connect. Basically, the way this token exchange works is I want to prove that some GitHub action, so some CI job that's hitting our server is reliable. It's who they say they are. It's coming up for for package publishing.
Yeah.
And so someone who's got control over the RP2040 repo should be able to publish to the atopile RP2040 package. That's what we're saying.
Yeah.
And the way this is awesome, 0 passwords, no tokens to set up. The way it roughly works is in the GitHub action, the GitHub action itself goes to GitHub and says, hey, give me a token. You pass that token to us. We go to GitHub with it again and say, hey, GitHub, is this legit? And GitHub gives us the thumbs up. And we're like, GitHub says it's cool. It's probably cool. We'll just do it from there and we're good to go. And it took me the good part of a day to get this all working properly in the end. And then I was like, this will be so much easier if I pull it out into a standalone repo. In the same case, like make it a smaller problem and I can get that development cycle up. And for me, it took me half an hour to spin up the repo, pre-commit, CI jobs, release, et cetera, the infrastructure and all. But I don't know how to do that for JavaScript in a way that's clean and will make and like understand how to build this visualization. Do you have like a framework that you typically have in mind of like, I use these end tools to build these visualizations fast?
That's a really good question. And because I'm coordinating like a lot of different contributors with very different skill levels, we do have like some very standardized things, but we build so much, we reinvent the wheel like maybe a little bit too much. So there's a framework we released for JavaScript called Graphics Debug, graphicsdebug.com.
Graphicsdebug.com. I will check it out. I'm literally asking you how to do this.
Yes. And what you can, it's kind of like a JSON object that is really obvious. So AI typically gets it right, and a little bit forgiving. And it can render to these really nice, like zoomable kind of visualizations. And so a lot of times we'll just say, hey, this is the interface you need to output. And then we can actually copy and paste that into our like either graphicsdebug.com or our like test suite, which is just the React component for graphics debug.
Oh, interesting. That's cool. So is it like an interactive canvas? Is that how you build something interactive like this little visualization with some lines?
Yeah, this is graphics debug right here, actually. So,
wow. And so this is all just a JSON description of what these lines look like then?
So in this case, I think it's a JSON description with, I think Claude might have added a little bit of interaction, but this is most, 99% of it is done by Claude. The mechanisms by which it does it, but it'll figure it out. Yeah.
Awesome.
I think that kind of stuff is important for stuff that's heavily CI or third-party API. I think that is harder to do, but is maybe changing with this whole MCP thing. Have you heard about this?
No. What's MCP?
So MCP is Model Context Protocol, and this is blowing up right now.
Oh, wow. Okay.
This was introduced a while ago.
Something introduced by Anthropic?
By Anthropic. And what it is you can kind of think of it as an HTTP API for LLMs, but it's very specifically made for their use case and how, like, it basically gives Claude, it integrates directly with Claude. So if you're a Claude user, you can just add MCP. OpenAI recently said they were going to implement or have support for MCP servers. So
awesome.
Basically, I'm simplifying a lot, I think. I haven't done this, but you can basically give a URL to your MCP, authenticate, and then Claude now just can do stuff for you. So people have used this to talk to their database and actually get data, do data analytics, talk to their Stripe dashboard.
You don't want to say the wrong thing. Like, hey, can you just clear that? No, not the whole database.
That's a huge problem, right?
Yeah, of course. But, very genuinely.
But it's really huge. There's I can't remember who makes this, but there's a catalog of MCP.
It's like Awesome MCP or something like that.
Something like that.
Okay, yeah.
And there's a catalog of MCP, and you can connect it to just so many things now.
Yeah.
And if you use Claude Desktop, I think you like literally just give it a URL and then suddenly
that's
can
awesome.
talk to it.
I'm going to have to try that for sure.
So maybe that can help with some of the authentication stuff, but authentication is always like such a mess.
I got it working, and I put it on Hacker News this morning. I don't think I got a single upvote. It's just very sad, but it is what it is. It's a really niche problem, but anyone who's wants to authenticate with passwordless login, etc. I made it.
Should we take a peek? Can I find it?
You can find it. It's I put it on a few hours ago, so it was a Show HN post. But
let's do it. Hold on. The only reason my article got on Hacker News, I give this guy full credit, but there's this guy Michael Lynch, and he wrote a blog post how to write blog posts that developers read, and I read it, was inspired.
Oh damn!
Wrote the post, and then we happened to his post, how to read blog posts that developers read, and my post both got on the front page at the same time. Hey. So I was like, hey man, thanks. That shit really works.
That's incredible.
It's a great article.
We don't need to go too much further with this, but you basically, you can make OACD fast API claims as easy as this, and then this is validated that GitHub approves this.
Nice.
And you just say like, hey, was it this repository that made this request? And either yay or nay, and then on the client side, you just do that. There's no
I like the abstractions,
Yeah, the middleware model that they have in fast API is really nice.
Yeah, I think GitHub is probably one of the more pleasant authentication handoffs. I think Google is like a nightmare.
Of course they are. That makes so much sense.
Yeah. I think Google, speaking of Google, and we were talking about Gemini 2.5 Pro, they kind of have like the worst chat interface. Have you used it?
By far. Have you tried to use their cloud SDK and interface?
No, I'm so like, I feel so burned on it. I
never
won't touch it.
Yeah, see, I mean, same, right? Like it's kind of the thing with Google is that they have a couple of core products that are done well, and everything else is brilliant in some way, and then just complete trash in something that they really needed to get it over the line.
Absolutely. And that's one reason I'm excited for MCP. I think what it'll do is make it so that I don't have to log into panels so much anymore.
So you'll be able to ask Anthropic to go ask Gemini for you.
Yeah, basically.
Do you think they're going to have providers or MCP APIs for other models? And so if you ask Claude something and it doesn't know, do you think it's going to be like, hey, I'm going to talk to my buddy 1 second, and it talks to Gemini and comes back?
I've never thought about this, but that 100% makes sense to me, because I would love to use like my local LLM that when I need to can go talk to...
It's Apple's pitch.
Yeah. Even 4.0, like I don't always need image generation, but they're the best for image generation right now.
Yeah.
So I would love to just like be using my little local model and do image generation with them.
Talk about mixture of experts. Like you really get at the top level something there too.
Yeah.
That'd be cool.
That's very exciting.
Don't mean to distract. Profiling. That makes sense. Yeah. Oh,
yeah,
that
you
is
get these good tree maps. How do you do this in Python? How do you
That's a
get
nice
tree
fire
maps
plot.
and like understand performance?
I typically use PyInstrument.
Okay.
Which is my favorite. There's another one that's somewhat, as with everything, rewritten in Rust, but I didn't quite find as good. So PyInstrument is my go-to, and it's a profiler in the same way that for 1 millisecond every 1,000 roughly, it interrupts the program, grabs the stack.
Yeah.
Sorry, every 1 millisecond, not that way. For some nanosecond, it'll grab the memory, inspect it, figure out what the whole stack was like and where it was, and that type of thing.
I feel like I'm a total noob to profiling, but that is the best way to do it. You don't want to have to this is how I was doing profiling, and if you're doing it like this, you're probably doing it wrong. You don't want to have to insert like a bunch of manual little lines that measure the performance of each function. You can get a utility like PyInstrument. Is that what it's called?
Yep.
PyInstrument, or the JavaScript Chrome profiler, and it will just tell you how much time is being spent on each line.
Yeah, where it's all going.
Yeah. And it just does that by kind of like stopping the program for a second or for a millisecond and looking at the stack.
They're even useful for debugging. There was someone in our batch who posted on our internal YC Slack and Slack engineering, hey, Python async help. And I was like, damn, this is finally one thing that I don't feel like, I'm out here at Atopile with 2 10x engineers as my co-founders. And I thought I was a pretty decent engineer. I'm a moron compared to both of them. Narayan in the electronics and Yanni in the computer science, they cross over a bit. They're well skilled. So when I could finally, and even amongst the YC batch, incredible people. So finally there's a question that comes up that little old Mac can answer. And thank God. And check out the profiler. And we use it as a debugging tool to get through this asyncio problem.
Oh, really?
Because okay, why is the asyncio like hanging? I don't know. Check the profiler.
Oh, yeah. So you can identify the hangups.
Like where it spent all this time at the bottom of the stack is probably the place you should go look.
Yeah. Yeah.
So they're super useful tools.
So good for debugging. Never use recursive functions. This is a spicy take. Ooh, well, all of these are spicy. The phrasing of all of these are spicy take. I don't know what mood I was in when I wrote this, but I was like, I'm just going to be ultra aggressive. Yeah. Never use recursive functions. So conceptually, recursive functions are kind of like a depth first search. You don't have much control over sort of the path of execution. You're always going to be calling it recursively and going deep before you go shallow. And there are ways to change it, but like really recursive functions are just not good when you're optimizing. It's just a lot harder to track iterations and all that stuff. So
that is a spicy take. We'll leave it today because I like being friends with you. But
Monte Carlo algorithms are hacks.
Absolutely agree with that one. I say that in the 0.2 compiler, we were just running basically a Monte Carlo to get the solver to work. And it was great. It worked. It was super performant. It was great in a lot of ways. But there are some humps you can't get over with them. And we avoided some big problems that we've now solved because we refused to.
Right.
Honestly, though, I think we might add a little of the randomness back because God, is it performant.
Yeah.
Oh, is it performant?
Yeah. And this was the cause of a lot of Twitter arguments because Monte Carlo algorithms super parallel. You can parallelize them. They're also kind of simple, and so when things are simpler, you tend to not like do stupid things. Like anytime you write code, there's a risk of doing something very very performantly bad.
Yep.
Most of my performance issues in the Autorouter were not like actual core algorithm things, but just
to take out the sleep.
Yeah, exactly. No, yeah, like these little weird things, like you're doing some data transformation and you actually accidentally did n squared inside of it, So, Monte Carlo algorithms, a lot of times I feel like there is a more rigorous method available because there's a very narrow, small group of problems where Monte Carlo is actually like best.
Yeah, no, that definitely makes sense. Have you ever heard of the Strand Beast?
No, Strand Beast.
Oh, you will almost definitely have seen them. They've been prolific forever. They're here we go.
Oh yeah, these giant kind of
they're these
wood structures that walk on the beach.
Yeah, I think they're like PVC tube even. I'm not 100% sure what they're made of, but I did see a piece on it the other day where they were talking about the algorithm he used back in the super early 2000s to work out the profile for the length of all of these linkages to walk, because you want a flat, you basically want a rotating input, a cam on the shoulder, and a flat profile at the bottom of the step, and then it pick up at the end of the step.
That's
and walk
right.
back.
Yeah.
But you want it to be flat on the bottom. And so he started off just thinking, oh, Monte Carlo, like we'll just randomize it. And then he ran the maths, and it was like, no, he said, well, this will finish when I get to the heat death of the universe. And instead wrote an evolutionary algorithm that would basically take these parameters, randomize them a little bit, make 1,500 variants, take the best 25, and then recombine.
Yep.
And it only took, I think he had to leave the computer running for 3-4 days to end up with a result that he liked. This was early 2000s. So,
right. Now it probably would be instant.
Now it wouldn't take too long.
He probably wouldn't even need to change the code. People would have just like optimized the Python or whatever.
Well, yeah. So incredible stuff, and there's better algorithms for it.
Yeah.
Completely agree.
Keep intermediate results grounded. This is the most like pro tip, just like, hey, do this. But you want to be able to inspect your pipeline, like, and figure out where problems started. And if you keep shifting things around, or your algorithms like operate in some weird space that isn't like physical space, like you suddenly stop using millimeters because you wanted to normalize or something, it's really hard to debug. So just keep everything in millimeters.
It's not
in
worth the
physical
trade.
Space. Yeah. And then you can overlay it and like see where things went wrong.
It really goes hand in hand with the visualize everything.
Yes.
It's imperative to do this in order to be able to even see what's going on.
Absolutely.
That makes sense. Yeah.
Animate your iterations to catch stupid behavior. Yeah. So this is probably this is one of the important ones. I think whenever you're optimizing, you kind of like computation, you can visualize what is going on at each stage. It's the same as profiling, but if you get a visual thing going, your human intuition can see, oh, it's getting trapped in a corner or something like that.
Yeah.
So just
go left.
Yeah, exactly. And then you can encode that human intuition in your algorithm.
Yeah.
This is a really good one. Intersection math is fast. You really need a grid. So almost everybody, when they're building autorouters, they like construct a grid and they do binary checks against the grid. This is like the number one technique in pathfinding. Like, okay, let's put everything on a grid. Let's figure out which grid squares are red.
Let's do everything as a bitmap.
Yeah, exactly. Do everything as a bitmap. But a lot of times you don't need to do that. It's like super non-performant to do that. Traces are almost always greater than like 50 microns. Right. So sometimes, especially if you have like two, like we have this thing where sometimes we have two traces, but they're crossing a really, really big space, and we've spatially partitioned to solve that one problem. You can compute where they're going to intersect in the vias very, very quickly using intersection math. To make a grid would literally take like many milliseconds. You can't spend that time.
No.
So
this reminds me back at the first company I started, we were making a CNC machine, and actually a lot of the same team here, Narayan and Sam with us as well, to a CNC machine that is easy to use as a 3D printer. So you'd give it a 3D model and a block of metal and be like, I'll be back soon. Make it good.
Cool.
Yeah. And there was a lot to that. Like, we had to reverse, back off and it's like, hey, this looks like a borehole, so we should probably make it precise and things like that. But the collision avoidance in the machine was the one that really think of here, where we actually went the other way, because it's not quite as true with 3D, and when you haven't got directly intersecting lines but bodies, it was a couple of gigabytes of RAM dedicated to these high fidelity binary blob. It wasn't a grid; it was a point cloud actually.
Yeah.
And because you also had to constantly modify the thing as you cut the metal, you had to remove basically points from the cloud. So you were just going through your RAM going 0, 0, 0, 0, 0, 0, 0, 0, 0, 0,
yep, at
a high rate, and that meant the intersections we could run in real time, thankfully. But it's with lines, a 2D map, so easy. Makes perfect sense. Makes perfect sense. Yeah,
3D math is a lot harder. I don't know if I would be saying the same thing if I had to work in 3D more often. Auto routing is really a 2.5D problem, where you get distinct layers and you're mostly doing 2D math.
Yep. Definitely. Yeah.
It's
In
very
2D space
interesting.
makes perfect sense.
I wonder if it's harder to visualize, but possible to do some of this stuff in 3D, but you would need a really robust visualizer.
I think you need to switch to, like, it doesn't make sense to try check the collision of lines either, because you could do it, but you're not going to end up with it very often. You almost want like a line and a plane or two planes or something.
Yeah. I think you mean in 3D space or
In 3D space.
Yeah, honestly, in 2D space, you're not usually working with lines. It's a simplification because lines have width.
Yeah. Yep.
So you're really doing segment to segment distance.
Yeah. Okay. Yeah. Interesting.
And so you would be working with like cylinder to cylinder distance would be the equivalent in 3D.
That's pretty interesting. That's a good point.
But but I wouldn't do it if you couldn't visualize it well, because I think with sort of a grid, a volumetric grid, you can visualize it. There is lots of ways to visualize it. With a bunch of geometric math, like, you're definitely limited by how well you can visualize it. This one's a little boring. Measure spatial probability of failure at each stage. Prioritize solvability. So basically,
Guess and check.
guess and check. Guess and check. You're probably gonna fail. So just like, if you see a stupid area, know about your stupid area at the beginning, so you can optimize it for it early.
Yep.
And then the greedy multiplier, the secret hack to 100x A-star performance at the cost of optimality.
Okay. Yeah. Go for it.
So I stole this one from game developers, and I put this little graphic.
It's the classic Arnie and it was in Predator. The Arnie
Is that what that's
handshake.
from?
I think that's what it's from. It was Alien versus Predator.
Oh, you're right. Yeah.
Arnie and the handshake. Game developers, auto routers.
So
Come together over pathfinding.
game developers have many insights about pathfinding because
makes
they have
sense.
to do it in real time all the time. And one of the coolest things that they do all the time is this thing, weighted A-star, which is basically you can make A-star suboptimal but execute way faster.
So suboptimal in the sense of the solution is suboptimal. Yeah.
The solution will be suboptimal. You won't get the perfect route, but usually it's like really close. And they've even analyzed how close it is to optimal.
Yeah. I'm sure there's a lot of computer science behind that.
And I call it the greedy multiplier because it makes your A-star more greedy. So if you don't know A-star is like just kind of like a grid search algorithm.
Yep.
And it's very simple. But
you can do it on a graph as well, right?
yes.
It's a search algorithm for any sort of discrete number of you can make a discrete number of turns at any point in your search.
Yes. A-star is so cool because really, as long as you have a cost function and a heuristic function, which is your estimated cost, you can execute it for anything. So we do this thing I call meta A-star, which is where we actually run like 50 autorouters in parallel, and then we determine the iterations that we're going to allocate to each autorouter using A-star. So we're like, how close are you? How many iterations have you used? Then we go, you've used too many iterations, and we switch to the next one.
You're expensive.
Yeah. And that's that worked out better than I thought.
Damn.
So A-star, super adaptable. And that's it. That's the 13 things to...
That's a heck of a blog post, Seve. I love that, actually. I think that's super sick. I'm definitely going to have to get into that. Is this all just based on Substack?
This is on Substack.
Hell yeah. Seve, thank you so much again. Love talking to you as
Matt.
always. I'll catch
great.
you soon.